Okay, so f of x equals x squared. I meant to write g of x there. And of course, f of x is x squared, but hopefully that's what you wrote. Okay, I think if you didn't get it right, you would have done that. So let's do g of x. So what's g of x? So g of x is 2f of x. And what's f of x? X squared. Okay. That one's pretty simple. H of x. H of x, yeah, write out what h of x is. It's f of x plus 1. Of course, there's no constant for that. Just copying down what was given. And now what's f of x plus 1? Well, f of x is x squared. So that's x squared plus 1. Okay. So it's as simple as it looks. Now this is less simple. K of x is f of x minus 1. Well, that means instead of x in the parentheses, we've got x minus 1 in the parentheses. If we got x minus 1 in the parentheses, that replaces x. And we replace this x with x minus 1. We see that this is x minus 1 squared. Now, this is something we spent a whole lot of time in class on Tuesday to do, and I'm not saying there's something wrong if you did do it. If you made a good attempt in the homework and it still didn't work, then you probably really need to, check it out with the mark. Ask me to explain it. Whatever, but this is really important, okay? Again, basically what I've told you about composites is if I write f with something in parentheses, then x becomes that thing in parentheses. And if this x becomes x minus 1 in this case, so does this x. And there it is. Okay. See if you can focus in that process. Okay. Anyhow, now we want to go on and talk about what the graphs of these functions might look like and how they might compare to the graph of x squared. And we're going to keep using composites. Hopefully things will become clearer. Sometimes, I mean, it's a new thing and it always gives people some trouble. It gives a majority of the class some trouble if they haven't seen it before. You should have seen it in prerequisite courses. But again, we're still recovering from what COVID did to our educational system. So you might not have. Anyhow, what I want you to do is go ahead and make a table for each of these functions. So I shouldn't have to write down the standard values. I'm just going to make the table using standard values. There they are in case you need them. Now you could complete this by saying y equals g of x and remind yourself, okay, that's 2x squared, right? And you could write down here, well, that equals x squared plus 1. And you write down here that equals x minus 1 quantity squared, right? Just, I mean, just so you don't have to keep looking back and forth. Of course, I took the paper away from you if you haven't written out. Just takes a minute to write them out. Okay. Okay, now we're gonna have to move on, but I gotta say that almost everybody is making really serious arithmetic mistakes. Okay. On adding fractions or multiplying fractions or squaring fractions. And even on plugging numbers in and getting results, okay? So you're gonna really need to focus on that. That's not something we can teach you. We just don't have time to do it. You've got to get that straight, okay? So make sure you do, because you're not gonna understand these transformations if you're having trouble doing this exercise, okay? So I'm gonna do it for you. Then I'm gonna recommend some problems for you to work on your own, okay? So you can see it happen for yourself. Because I'm gonna show you, but you're not gonna understand it like you would if you were seeing it happen for yourself. A couple of you actually got pretty good results, okay? But most of you had a problem with it. Okay, so anyhow, we're doing 2x squared, okay? Well, if x is -2, then 2 times -2 squared is 8. I don't have room to write out all the arithmetic, but yeah, I'm not going to be able to do the graphs on this board anyway. So I'll just write a little bit of arithmetic up here. Now 2 times -2 squared means 2 times -2 times -2, which is positive 8. 2 times 2 is 8, and 2 negatives make a positive. Okay, so, you know, not everybody is getting that much, so you really need to pay attention or do some review. Anyhow, 2 times -1 squared is 2. 2 times -1/2. Well, we've got two fractions, they're both negative, so you're gonna end up with a positive. That's gonna equal 2 times 1 over 2 times 2. I'll do 1 times 1 over 2 times 2. You multiply the numerators, and you multiply the denominator. And that's gonna be 2 times 1/4, which is 2 times 1 over 4. Make that 2 over 1 times 4, so it's 2 over 1 times 4. Now, I'm not writing that out real coherently. That's 2 over 4, and that's 1/2. There are several steps that you go through to make sure that you've got 2 times -1/2 squared. You square -1/2 using the rule for multiplying fractions, which you absolutely need to know. You're going to have to do it with symbols before too long. Okay, and the symbols can get complicated. You have to have these rules down. And then I can write that, of course, 1 times 1 over 2 times 2 is 1/4. 2 I write is 2 over 1. It's a little hard to see that. And then I got 2 times 1 over 1 times 4. And that's 2 over 4, which is 1/2. You need to understand every step of that, because when you have to do symbols, you need every step. Okay. So there's plenty of stuff in open math we can review fractions. You go to a half credit page and do the assignment of fractions. If you need more practice, let me know. I can provide you with exercises or link to a place where you have exercise with answers. So make sure you're doing it right. Okay, so anyhow, we get 2 times -1/2 quantity squared equals 1/2. 2 times 0 squared equals 0. Of course, 2 times 1/2 squared equals 1/2. It's just like 2 times -1/2 squared, except you don't have the negatives. They go away in this step, and then everything's the same. And then you have 2 times 1 squared is 2. 2 times 2 squared is 8. Okay. Now h of x is x squared plus 1. For reference, I've got a table for x squared. Okay. And this is a table everybody needs to be able to make instantly and sketch the graph. Okay. Without memorizing that 1/2 squared is 1/4, understanding why 1/2 squared is 1/4. Among other things, every other number is pretty easy to find. You just got to remember if you square a negative, you're going to get a positive because a lot of people want to square a negative and get a negative. Okay. So if we have this table, it's easy to just do the table for 2x squared. Now, I wanted you to do the table for 2x squared without this, but if we look, how does 2x squared compare to x squared? Well, it's twice as big, right? So if x squared is 4, 2x squared is 8. If x squared is 1, 2x squared is 2. If x squared is 1/4, 2x squared is 1/2, and so forth. Okay. Well, we can easily get the graph of h of x. H of x is just x squared plus 1. I'll just jot it down here because I don't have time or room to do this. Okay, you can do the arithmetic, get -2. Well, -2 squared is 4, and add 1, you get 5. Arithmetic's real simple here. And without going through it all, I can just refer back to this table and add 1 to everything. Okay. So for -1, you're going to get 2. And -1/2, you're going to have 1/4 plus 1, which is 5/4. And since we're going to be graphing it, we might maybe write that as 1 1/4. For a 0, we're going to get 1. For 1, we're going to get, we'll write it as 1 1/4. Uh-oh, I didn't do 1. Okay, never mind. This is for 1/2. For 1, we're going to get 2. And for 2, we're going to get 5. Okay, now let's just stop for a minute. How's the graph here going to compare to the graph here? Well, every y value is going to be twice as much. So at every point, at every x value, the graph is going to be twice as high. So if your x squared is here, your 2x squared is going to be steeper. It's going to kind of look narrower too. Okay. Yeah, we go through the details of graphing it. And the x squared plus 1. Every point of the graph is just going to be 1 unit higher, isn't it? We're just adding 1 x squared. Now, we talked about this at the end of class last time. So I don't want to go too much into detail on it, but these two are easy. Okay. I was going to have you graph them, but people took a long time to do the arithmetic, made mistakes, so we aren't able to do that. This is why I'm going to ask her to do a couple of other exercises. I have showing all the details. Okay, so what about this k of x? This is quantity x minus 1 squared. Okay, well, if x is -2, that means we're going to have -2 minus 1 squared. What's -2 minus 1? Well, it's -3. And if that isn't completely obvious to you, you need to look at how to add things on the number line. There's a simple picture that you go 2 this way and you go 1 this way. That means you went 3 this way. Okay. So I have to do that. You square -3, you get 9. If x is -1, get 4. I can't write all of these, I need to work them out. If x is -1/2, then you get -1.5, which is -3/2 squared. You're gonna get 9/4 or 2 1/4. And if x is 0, you're gonna get 0. If x is 1/2, you're gonna get -1/2 minus 1 squared. Uh-oh. I made a mistake in this one. Because if you do -1/2, negative of -1/2 is +1/2. This gives you 3/2. This is the one that gives you 9/4. And then okay, I'm messing up something. In my arithmetic too fast. Okay, if you put in -1/2, you're going to get square of -1/2, which is 1/4. I've got to write that out. Somehow doing it in my head isn't working. Okay, the negative of -1/2 minus 1 is 1/2 minus 1, which is -1/2. And if I square that, I get 1/4. Talk about doing arithmetic right. Okay. Let's do this table correctly. And I apologize. Okay, you got x okay. X is -2. Y is -9. X is -1. You get -1 minus 1 squared, which is -2 squared, which is 4. If x is -1/2, you get -1/2 minus 1 squared, which is what I said originally, 9/4. I don't know what I did to confuse myself. Okay. I was doing an extra negative because I wasn't writing it out. Could do that, but I did. Okay, and then you get 0 minus 1 squared, which is 1. And at 1, you get 1 minus 1 squared, which is 0 squared, which is 0. At 2, you get 2 minus 1 squared, which is 1. And I didn't do 1/2 And I don't really want to see that in there, so we can do it. Okay. 1/2. 1/2 minus 1 squared, which is 1/4. At 1, we get 0, and 2. We get 2 minus 1 squared, which is 1. All right. The thing I want to really look at, it's easy to do these graphs and see how they work. There's a lesson in this graph, and that's what I really try to get at. In my usual graph, I hope everybody understands by now what these marks mean, because we've used them a whole lot. I'm going to have to extend my y-axis up higher. I'm going to put 4 about here. So the 2 is going to go here, 1's going to go here, and we're going to have 1/2 and 1/4. -2 gives us 9. Now 4 is here, 8 is here. 9 is up here somewhere. So here is our point. -2, 9. Now that's new when we do the basic function graphs. We never got a 9. But now that we're doing x minus 1 squared, that's not one of your basic toolkit functions. But it's closely related to the square function. Okay. If x is -1, we get 4. There it is. If x is -1/2, well, we get 9/4, and that's 2 1/4, and that's going to be up about maybe here, a little more than 2. At 0, we get 1. When x is 1/2, we get 1/4. When x is 0, we get, I'm sorry, when x is 1, we get 0. And when x is 2, we get 1. Now, what's the plot of this graph look like? Now we come down here like so. Now, from here to here, isn't that just kind of a cutoff graph of the x squared? Okay. This is the x squared graph that shifted 1 unit to the right. So what we see is, without doing all these graphs, because I kind of did a couple of them last time, but if we do 2x squared, all the points in the graph get twice as far from the x-axis. So that just stretches the graph out in the vertical direction, as we talked about last time, as you're going to see in the open math assignment. H of x just adds 1 to x, that just raises every point up 1 unit. Go back to what we did at the end of last class, we sketched that sort of thing. Okay. K of x, on the other hand, there's something a little bit weird. You're squaring x minus 1. It looks like if that's going to move it, it's going to move at -1 units. Okay. But what really happens is, to get the same numbers, x has to be 1 bigger. Okay. Like, you get 4. We would ordinarily square -2, right? Well, -1 is 1 unit to the right of -2. So when we square -1, when we square x minus 1 squared for -1, we're actually squaring -2. Okay. So if we were comparing this with a graph of y equals x squared, every point would be 1 unit to the right. This point is 1 unit to the right. -1, 4, we can verify is 1 unit to the right of -2, 4. And we can make that comparison by quickly, we don't really need a table, I hope you know. Sketch a graph of the x squared function. It's going to look like this. You see that every point of the x squared function has moved one unit to the right. That picture makes sense. So by replacing x by x minus 1, everything moved 1 unit to the right. Now there's some rules for these transformations. A times f of x moves every point a times as far from the x-axis. So that, for example, if you have the graph of x squared, I'm going to draw this without doing any points. Here's the graph of x squared. As we saw last time, points on this graph all move twice as far from the x-axis. Notice that this point doesn't move as far as this does, right? Why? Because it's not that far from the x-axis to start with. Okay, if it moves twice as far, well, it doesn't have that far to move. Okay. Analogy. You've got $5 and you've got $20, whoever you are. Okay. One person has $5, one person has $20. If you double their money, who makes more money? Whose money increases by more? Well, if you double $20, you get 40, you get 20 extra, right? You double $5, you only get an extra 5. Okay, it's just kind of like this. That's like $5 being doubled. That's like $20 being doubled. You gain this much, but here you only gain this much. You really want to understand that. Okay, and you know, do the same here, do the same here. So if you double every value, it's like you're stretching the graph out in this direction. Okay, we call that a vertical stretch. Now, what I told you is a lie, sort of, and intentional. If A is negative, How do you move something negative 2 times as far? Well, you can define that, but if A is negative, you flip the graph over, all your values become negative, your graph goes upside down, then you double up. Okay. So I'll say, here's the graph, absolute value of A times as far. And I'm not going to write it in because you're going to see it. But it's going to reflect the graph through the x-axis. Okay, so for any f of x, we have this. We also have this. There's every point A units in the vertical direction. So if we have again our graph of x squared, every point moves the same distance. So whereas before, this point didn't move as far as this point will move as far as this point. Maybe we need to make that arrow just a little longer. Okay. And the graph has exactly the same shape. This graph doesn't have exactly the same shape. The other graph is vertically stretched. It's kind of looks skinnier. Okay. This one has exactly the same shape. I didn't draw it very well, but it's drawn right, it will. Okay. And if you complete the exercise and draw the numbers on these tables, you're going to find the same thing. You're going to find that your k of x, so it's actually that would be your h of x function. We usually use k for this number. And that has nothing to do with the k of x we used before. Okay. Now, okay. Then f of x minus h is every point 10 units in the horizontal direction. And that's just what we saw here. So among other things, we could move this point out here. Now this would correspond to x4 to 3. And it would be up at y equals 4, because on the standard x squared graph, your y coordinate here is 4. So the y coordinate on the shifted graph ought to be 4, when x equals 3. And we could calculate that. We could extend the table. It's really easy to see that's correct. Okay. Well, that's the whole idea of transformations. And I'm going to ask you now, debating which graph I want you to do. Gonna be either the reciprocal function or the square, or the exponential. I'm just say, take the basic exponential function, look at exponential function, and sketch me a quick graph. Then we're going to ask you to do some transformations. And again, you just have to always know what these functions are, how to make the table and graph in a short time. It's not something you learned 3 weeks ago and forget. These are the functions that the whole course is built on. I'm going to remind you again, I'm going to stop reminding you. You understand? You need to know these functions thoroughly. Only 3 of them at this point, and then there are going to be 2 more very short. Then there are going to be a few more that aren't as important. Let's go back. Okay. Got no names. Who did the X function? The values. You know what a negative exponent is, and you need to. It's going to be all over the place there. Okay. Then it's the simplest of all of the 3 graphs that we've looked at. So there's your table. Make absolutely sure you know how to calculate these and you know what the names of the functions and the formulas are for the functions. This is a function that's going to govern your financial life for the next 60 years. Okay? Hopefully more than 60 years. Who knows how long people are going to live if we don't kill ourselves first. Okay. And we could, right? You got to watch that. Okay. Okay. Now, not you. As I just said, don't be offended, but we had to spend way too much time on simple arithmetic, and even on things like 1 should be twice as close to 0. Okay. Subdividing, which will be done numerous times. You really need to understand that so you can do a graph of your exponential function. It has the right shape so you can see how these transformations work. Okay. If you can do this accurately, and do what I showed you how to do here with the square function. Just adapting it to slightly different numbers. It's -2 instead of +1. Okay. And this is -2 instead of -1. But it's practically the same thing we did here, just applied to a different function. Of course, you need to read your text. And then review whatever parts of the video you aren't sure that you completely understand. Or if you can get it from open math, okay, but I want you to understand it. So please work on that. Okay. And almost everybody isn't doing their fractions. Okay. You gotta know the rules for fractions. I've emphasized that before. You're gonna have to know when we do symbols before you really want it to. Okay. If you don't internalize those rules that you learned in 5th grade and forgot because they put a calculator in their hand and let you bypass the thinking process, the mechanical process that you didn't understand. Okay. And you're at a disadvantage to do that. But it's 5th grade math. Okay. Get it down. You had it down in 5th grade. I'm not asking you to do anything that you don't already know how to do if you practice it. Okay. Move on, and please do what you can do on the assignments. Okay, I see too many assignments. Because the only points people get are the points where it asks if you just reviewed this. Okay, and then I look and you spent 30 seconds on it. Okay. Most of you aren't doing that, but there's a tendency, some people do that. Okay. Maybe talking in general. I don't see a whole lot of that from this class, but I've seen a little bit of it. Okay. Don't claim to have reviewed something that you haven't reviewed. It's there for a purpose. It's there to give you the information you need to do the problems that aren't going to tell you. Okay. Do the problems honestly. You know, if you have questions, there's a good chance I'm going to ask you to do something else. That's more work, but if you need it, you need it. Okay. So please get into the problems. If you're not doing them, some people aren't even opening things before they do. Okay. You have to do these problems. And you have to show me where it is you're having difficulty so I can. Okay. Because a lot of times the difficulty, I think I cleared up one problem earlier today. Took like 2 minutes. Okay. So what's necessary? Okay. Look forward to seeing you Tuesday. Good luck on the assignment. Okay. Everybody did pretty well on the homework. I think the only mistake I saw was somebody, don't remember who, had an interval from like 1 to infinity. Should have been an open interval and they had it closed, which gave them a division by 0. Okay. So if that's the only mistake we got, that one's easy to fix. So pretty well happy about that. Hope you are. Okay, we'll move right on to the idea of arc length. So I'll give you the curve. Okay, x squared I plus 2xj plus 3k. And first I ask, how far is it from R1 to R2? Give me a minute to work that out. Well, you're right, okay. But if R is 1, it is 1, 2, 3. And if R is 2, it's usually 1, 4, 3. Right. Well, compared to here's 3, compared to here's 2, compared to here's 0, use the Pythagorean theorem. And we get the square root of 13. Okay. Okay, well. How far from R1 to R3 halves? How far from R3 halves to R2? And if you're viewing remotely, participating remotely, should just be viewing. I've opened the chat window, so you can ask me to write bigger or more clearly. I'm not sure exactly how this is coming through. At a distance. I think that should be legible. If not, let me know. Okay, you're gonna ignore me because I didn't have a recording on that I did this, but I estimated the distance square root of 13. Okay. And I kind of thought the square root of 13 is around 3.6, closer than I thought it would. Then we want to do the distance from R1 to R3 halves. And we work that out, and it's very straightforward. We get the fractions, square root of 41 over 4, which I estimated to be 1.6. Okay. Turns out my estimates were really close, even the way my brains work today. I'm surprised. Okay, I'd be surprised if we get estimates that close. But then from from R3 halves to R2, now we calculated here, very straightforward. Again, if anybody has any questions, let me know, but I think we pretty much got it. And I estimated 2.02, fairly easy estimate. Square root of 65 is pretty close to 8.1. So I lucked out on this estimate, because what people got was 3.61 from this point to this point. Okay. 1.60 from here to here, 2.02 from here to here. We didn't do a third significant figure. If we had, we would have found that the sum of these is a little bigger than this. That's because this thing has some curvature. Shortest distance is a straight line. This is your straight line distance. Now this is a point to point and then point to point distance, where this point lies along the curve. So the sum of these distances can't be as small as this distance if there's curvature, and there is, because then t squared. Okay, so the distance of the curve is bigger than the distance between any two of the points. Okay, well, now we could draw a graph how this is in y versus x. It's going to be like a parabola here. If t is negative, then actually the I should still be positive. It's going to look like this. It's going to be a parabola on its side. And that doesn't matter. We're just looking between 2 points of this curve, and we see that there's a curvature. This might represent t equals 1 and t equals 2 points. Go from R1 to R4. There's a curve spot. Okay. So we're going to use that interval. We're going to try to figure out how far it is so we can actually follow this path. Okay, so along this path from R1 to R4, t is going to go from 1 to 4. It's a no-brainer. Okay. Now, if t is time, then what's the speed? Well, what's the speed? Let's see what we got for speed. Okay, again, I forgot to stop recording. I don't know exactly where I stopped, but if t is a time, then the speed is the magnitude of the velocity vector, and velocity vector is the derivative of the r vector, which is this, which equals this, which equals this, and that's really straightforward. So if you have a question on it from here or out there, throw one in the chat. Say, you say that again, okay? Everybody okay with that? Okay with that? We just been through it. Okay, so if I take this arc from R1 to R4. For R1 is like vector 1, 2, 3. So this is like point 1, 2, 3. This is the point 1683. I should fill in the speed. So I just plug in article 1 here. Okay. 1 and 1 is 2 squared, and 2 is about 1.4. 2 times that's 2.8. Okay. And then if t is 2, and that'll be the speed at this point, and 2 squared plus 1 is 5. Square root of 5 is about 2.2. All that, you get about 4.4. It's probably close to 4.5 when you do all the best. Get the idea. So evaluate the speed at this point, this point, this point, this point. And say, okay, let's get an average speed. And multiply it by the time interval. Assume like maybe you don't have to have units on your time here because it's really just a parameter. We'll see what it is right now. Doesn't matter if t has a meaning or not. If we interpret it as time, let's interpret that as seconds. 1, 2, 3, 4 seconds. Then the average speed between here, say the average of this and this, and notice that this is just 1.6. This is just about 1.6 more than this. This is 1.8 more than this. This is 2 more than this. The speed is increasing, we're accelerating along this curve. Okay. If the average speed along here is the average of 2.8, 4.4, which is 3.6, time interval is 1 unit. That means your distance would be 3.6. Averaging these two speeds, the average speed is 5.3. N times 1 second gives you a distance of 1.3. The same thing here gives you a distance of 7.2. You add those up. If I add it right, I got 16.8. So is that plausible? Is that a plausible way to figure out the length of this curve, the distance along the curve? Straight line distance from here to here. That should be less than the distance from this point to this point. Okay. But if I work it out, here's the R1 point, here's the R4 point. Right there is the theorem applied to displacement of 15 and displacement of 6. Okay. I think we get the square of 261, which is a little less than, oh wait, that's a little more than it's 256. Okay, that's pretty close to 16.1. Okay. Now, that got us a question of, are we overestimating or underestimating the average velocity? Okay, I'll leave that question. I kind of underestimated some of these speeds. Okay, 4.4 probably should have been 4.5, and so forth. So there are uncertainties there. These are very comparable. Straight line from here to here should be a little less than this distance, not a whole lot less. So our estimates coming out the same, given that these were done by mental calculations, by a mentality of questionable competence. Okay. It's at least a plausibility argument. The idea of interpreting speed, velocity, and so forth. Well, in that case, we integrate the speed from one time to another. We get a distance. Well, that goes back to calculus physics 1. And of course, not everybody's had physics yet. But yeah. Okay, that's, you integrate how fast you're going, get how far you're going. I will see if that's really true in this case. So, what we want to do now is we'll make this a little more rigorous. And say, okay. I've just partitioned the interval from t equals 1. Have 0 there. T equals 1 to t equals 4. And you could say, okay, well, you can visualize the time axis. Doesn't really have a whole lot to do with this curve. But you can still say, okay, here's 1, here's 4. So we just split up this time axis. And here is the ith interval. Of our partition. Here's a partition. Partitioning the t interval from 1 to 4 looks like this. Typical interval, call it the ith interval. All we have to do is figure out what happens on the ith interval and then do some limits. Then we get an interval. I agree with this. Well, the ith interval of partition. Take this interval. And enlarge it. So here's EI. Actually, it's TI minus 1 to TI. That's what I should have done it up here. Write it down fast for that. But the ith interval, the first interval goes from T0 to T1. It ends, interval number 1 ends at T1. Interval number 2 ends at T2. Interval number I ends at TI, whenever TI happens. Okay. Then we do a sample point in here. Not sure what location you use in calculus. We have some notation for something. I shouldn't. So I'm using TI star for the sample point, and this could be any point in this interval. It doesn't have to be the midpoint, because it doesn't matter, because we're going to shrink these intervals until it's 0. And if the interval is small enough, the thing we're integrating is going to change much between here and here. It doesn't really matter where you take your sample point. Okay. And that can be done much more rigorously, but nobody's doing that these days, so we're not going to do it. Plus, you know, everybody in this class is going to be an engineer. Engineers usually don't worry about the fire points. Mathematicians say physicists don't usually worry about the fire points. And, engineers accept fire points unless they go real deep into mathematics. And we can just accept that we can use this as a sample point to get a reasonable approximation without going into all the upsides and deltas and everything else gets skipped in many calculus courses. I know Will did it in his first semester. It's still not emphasized. So we're not going to do it. Okay. The idea then is we multiply let's write this out just a little more. Okay. Now, and our prime change the rate at which R changes with respect to T. Wave my hand a little bit with this approximate change. In R. Okay. Specifically, that means whatever T is here, evaluate R at that T, and then multiply it by a small delta T. It'll tell you the change in R. That's something that kind of comes out of what you did for homework. You know, the way these vector functions were analyzed with limits and all that stuff. Okay, so directly relevant to that. Again, don't worry too much about it. But there it is. There's your approximate change in R from the interval delta T. So magnitude of this, well, I mean, it's like you got R of T down R of T plus delta T. Here's the delta R. It's approximately equal to R prime of T delta T, just by all the definitions and by the meaning of displacement. Okay. And of course, R prime of T is defined by the difference function. It's a limit of R of T plus delta T minus R of T over delta T. Well, that's exactly what this picture is saying. So that I'll put the word approximate in there. Okay. That should make sense. You need to ponder that until it does. And you need to go back and ponder calculus 1 until it makes sense there too. Okay. It's going to need to make sense in this course. Okay, now I'm using T as time. So time T is interpreted as time, then the R prime of T is like your velocity. And we're just leading up to that integral there, except it's going to be the integral of R prime of T. Negative R prime of T. what I've said here would make no difference at all if I use the letter U in my parameter. Okay, with R of U, it would still be true that R of U and R of U plus delta U differ by delta R equals R prime of U times delta U, where U doesn't have anything to do with velocity. U might even be the distance along the curve, and it will be in the later example. Okay. Well, staying with the idea that, okay, we're going to just interpret this as time because it doesn't hurt to do that. It's going to work for any parameter. So if the parameter happens to be time, it's more intuitive than other possible parameters. And so, and the distance on the ith interval said approximately equal to R prime of T I star. In other words, evaluate the speed at some point in here. But this is a small interval, the speed doesn't have time to change very much. It's R prime of T delta Ti. Of course, that's a vector. Magnitude of that vector. And delta Ti, what's delta Ti? Ti minus Ti minus 1. And we press that as delta T. But the sum of the magnitude of R prime of Ti times delta Ti. And the sum goes over our partition. This will be the sum oh man, I've been ready by hand. Sum from I equals 1 to n. And where n is number of intervals in your partition. Okay. Now, if we assume we use equal intervals, we can then say, just let n go to infinity. That just switch all these intervals down. So where the error we have, whatever error occurs, whatever uncertainty occurs because of our position of Ti star, that disappears. Because our intervals approach 0. Ti star is squeezed between Ti minus 1 and Ti to the ultimate extent. Put my hands a little bit, okay? And all these approximations, the error in these approximations approaches 0. In each approximation, the percent error in each approximation approaches 0. So the percent error in the whole approximation approaches 0. And then this approaches the interval from T naught to Tf or Tn, but T naught is 1 always, and Tn is always 4. So it's integral from 1 to 4 of this expression. Okay. Now your delta T is just a constant for each interval. So for each interval, you can pull that delta T out of the absolute value of the long side. Okay. Then you get the result. And a lot of board space, as always. But from this development then, these details, make sure that was all visible. Have to put any adjustments. In the cloud, or from individuals. Put this right through this. Okay. Can't call them by name. Like to be able to call people by name. Privacy laws have their trade-offs. Okay. Well, then the arc distance. Equals the interval from 1 to 4 of magnitude of r prime of t no longer relative to its dt. So it's a simple integral. It could also be written as the square root of r prime of t times r prime of t dot r prime of t. That's how you get the magnitude of the vector. For operations, as opposed to Pythagorean theorem. Okay. Comes out the same, so it doesn't really matter which one you use. And in this case, for r prime of t, which we calculated earlier, is that is square root of t squared plus 1 dt. So work that out independently, work it out, and see how close it came to the straight line distance. Good exercises. Make yourself a note to do that. Okay, this is a general way to get it. Now let me just check something out here while you assemble some notes. Start with the idea that the curvature of a circle is 1 over r. Okay. Now, let's say r equals cosine theta I plus sine theta j. Okay. And let's Actually, go ahead and use T, so we think about time. So before I do this, now, A times the cosine of T, this is sine T. It's A times cosine T of I plus sine T of J. So if I take these circles, which circle has a greater curvature, circle 1 or circle 2? You write down the expression for the curvature of the first circle and the curvature of the second circle. So this circle, I say this is A1, grade is A1, this grade is A2. Okay, so ask which one has a greater curvature. So write down the expressions for the curvatures of these circles. Okay, so we define curvature, the circle of radius R is 1 over R. That's our definition. If I have a circle of radius A1 and a circle of radius A2, where A2 is clearly smaller than A1, maybe about half of A1, which one has a greater curvature? Well, by the definition, 1 over R, 1 over A2 is bigger than 1 over A1. Because A2 is smaller than A1. Okay, then of course this means I'm driving my car around these circles. Okay, now I threw out the question, kind of a trick question. I'm driving around these circles, and which one am I going to have the greatest centrifugal acceleration? Okay, which one is going to be harder to hold the car in the curve? Well, obviously, the sharper the curve, or the less the radius of curvature, the harder it is. If I'm driving at the same speed, never said I was driving at the same speed, so you actually couldn't answer the question. But the best answer you could have given would be with a small one. If you had to give an answer, that would be your answer. But you have to qualify that. Only if the speed is the same. I mean, you know, not always necessarily know this, but centrifugal acceleration is like V squared over R. Okay. So little change in velocity has a big effect. But yeah, if I could just barely hold the car on this curve, I'm certainly not going to drive around this curve at that same speed. I just get the intuitive idea of curvature. It's also related to centrifugal acceleration, which is related to the second derivative of the position function. So we talked about it. Okay, so anyhow, okay, so R is, let's say A cosine of the A times the quantity cosine T height and the sine T day. Of course, we could have a K component. We could be going around a helix. We would go on a helix that, like we saw last time, that spirals faster and faster upward. Okay, not really mathematically correct use of the word spiral. Understand what I mean? So you would have a component of your acceleration upward as well as a component inward. All right. Well, let's just define the curvature. I'm going to claim the curvature of either of these circles is calculated. Rate of change of your velocity vector But again, if I'm driving faster on the same curvature, my velocity vector is going to change faster. But its curvature hasn't changed, so we can't just say it's the rate of change of your velocity. Rate of change of velocity vector divided by your speed. And now what happens to your velocity vector around this curve? You have velocity vector here. You have a velocity vector here. Run around the curve this way. I defined it. The rate of change of velocity divided by speed. Rate of change of the rate of change of velocity. It's the rate of change of r double prime divided by speed. It's your second derivative corrected by how fast you're going. Second derivative is going to be inward if you're driving a circle at constant speed. Second derivative, that's going to be your acceleration. That's going to be some trick. It's going to be towards intuitive. And we can make it rigorous. Okay, so I said that would make sense. Okay, that's the magnitude of the second derivative divided by speed. So we want to verify this with this function. Well, pause this for a minute. I think I'm saying something wrong. And you can hold. Okay, I don't know if I recorded what I did there, but I just, realized I was telling you something. Okay. And I'm going to verify on the circle. And what I was going to write down, magnitude of r double prime divided by the magnitude of r prime, which is going to give me 1. Okay, and I couldn't be right. So the thing, okay, again, you're going around this circle. What's really happening as you go around the circle is your direction of motion keeps changing, right? So if I'm on the circle and going in this direction, shortly thereafter, I'll be going like the solve the vectors that I have written here in the delta V. Okay, and that delta V in the limit gives you your r prime. Okay. Your r prime defines your direction, but can't be taken to be the quantity. It gives you direction. It gives you direction as your unit tangent. You take a vector length 1 in your direction of motion. How fast does that thing change? Because your velocity vector is going to change faster if you're moving faster. Your unit tangent vector is not going to change. Your unit tangent vector is always going to be tangent to the surface. Okay, you just drive around circles for a while. And convince yourself of that. The rate at which scenery goes by you is greater you have a greater velocity. And you see a velocity vector, well, it's changing faster. So your direction motion is changing faster if you move faster. Okay, so we're just going to say it's the rate of change of your direction corrected for your speed. Okay. That makes sense? Hopefully it makes intuitive sense since I garbled it. But, direction is indicated by your unit tangent vector. So R here. Basically, rate of change of unit tangent vector is R. Okay. The unit tangent vector in this case would be negative sine theta plus cosine theta. Its magnitude is common. Now we take the derivative of this and divide by magnitude of the derivative, which is A, and you get just that. Okay. Here that comes down to 1 over A, because the magnitude of R prime is just BA. Okay. So, well, you have curvature, which you can calculate. The simple formula is easy to understand. You understand what I'm telling you. Okay. Just take whatever curve you're on, you take the rate at which you're using tangent vector, and you just divide that by your speed. The radius of curvature means you're going around a curve. Okay, the curve's not an arc of a circle, but temporarily it is. Any curve, there is at any point, there's a circle that which they oscillates through. I just love to do the equation of the oscillating circle. Take it easy, on you this year. Okay. Speak of the sign goes. Okay. And the curvature of this circle is the same as the curvature of the path at that point. The curvature is not particularly difficult to calculate. Neither is arc length, at least from the problems that I see on the website. Of course, they have this to get out of hand. Integrate the square root of t squared plus 1 is can't really be challenged. Okay. Incidentally, if you can't integrate that, go ahead and use Wolfram or something, find out what the integral is. See how it compares with our estimates. Be sure you do that. These are some intuition. So understanding this should hopefully lead to understanding this. Despite the fact that I screwed it up a couple of times. Hopefully you got the picture. Like formulas are easy to use. But understand what the formulas are. Okay. Okay, any last minute questions? If